If you've trained a diffusion model or flow matcher, you've essentially been estimating a transport map. But here's the catch. Nobody actually targets the optimal transport map. And a new statistical framework just proved why that's not just a computational shortcut. It's a statistical necessity. Let's break it down. In optimal transport, you want the map that pushes a source distribution to a target distribution while minimizing a cost, typically the squared Euclidean distance. That's the optimal transport map. But computing it from finite samples is notoriously sensitive to perturbations, especially in high dimensions. So modern generative models learn any valid map that satisfies the push-forward constraint. The natural question is learning a suboptimal map statistically easier? Researchers formalized this using a minimax risk framework. They defined a valid map loss that measures the squared L2 distance from your estimator to the entire set of valid transports, rather than a single canonical target. The first result. Under strong stability assumptions, like when the Brenner potential is smooth and strongly convex, estimating any valid transport map is statistically just as hard as estimating the optimal one. The minimax risks are tightly sandwiched. Stability essentially guarantees that Wasserstein errors in distribution estimation translate directly to map estimation errors, making suboptimal targets statistically redundant. But when stability breaks down, the gap explodes. By constructing adversarial geometries, the authors demonstrated polynomial and even exponential separations in minimax risk. In these unstable regimes, the optimal transport map encodes fragile global matching structures that become statistically irrecoverable from finite samples. Meanwhile, alternative valid transports can bypass that fragility entirely, learning at drastically faster rates. This isn't just measure theory. It rigorously explains why flow-based and diffusion models thrive on real-world data, which rarely satisfies convexity or density regularity. Targeting suboptimal maps isn't just about tractability. In unstable regimes, it's statistically superior. If you want to understand the fundamental limits of modern generative AI, tracking these transport stability boundaries is exactly where the next breakthroughs will happen.